Welcome to the Midnight Lesson. Tonight, we are exploring one of the most powerful and restless features of our planet, a vast, invisible boundary that circles the Pacific Ocean, shaping continents, raising mountains, and unleashing earthquakes and volcanoes with little warning. If you have ideas for future topics you would like to fall asleep to, feel free to leave them in the comments. Your suggestions help shape what we explore next. Now, settle in, get comfortable, and let your thoughts slow as we begin our journey into the Pacific Ring of Fire. Chapter 1. A Circle of Instability. The Pacific Ring of Fire is not a single place, nor is it a visible structure on the surface of the Earth. It is a broad, horseshoe-shaped zone of geological activity that stretches for more than 25,000 miles around the edge of the Pacific Ocean. Along this immense arc, the Earth is constantly in motion. Tectonic plates collide, separate, and slide past one another deep beneath the surface. These movements generate nearly 90% of the world's earthquakes and more than 75% of its active volcanoes. Despite its dramatic name, the Ring of Fire is not defined by flames or molten rock at the surface. Instead, it is defined by pressure. Slow, relentless pressure that builds over decades, centuries, and even millions of years before releasing its energy in moments that can reshape entire landscapes. This ring begins along the western coasts of North and South America, where the Pacific Plate meets smaller oceanic plates. It curves northward through Alaska and the Aleutian Islands, then sweeps down across eastern Asia through Japan, the Philippines, and Indonesia, before continuing through the South Pacific toward New Zealand. Each section of the ring behaves differently, shaped by the unique interactions of the plates beneath it. Some regions experience frequent, small earthquakes that gently relieve stress. Others remain quiet for long periods, silently storing energy until it is released in powerful, destructive events. To understand why the Ring of Fire exists at all, we must first understand how the surface of our planet is organized. The Earth's outer shell, known as the lithosphere, is broken into massive slabs called tectonic plates. These plates float atop a softer, hotter layer of the mantle, moving slowly at roughly the speed that fingernails grow. The Pacific Plate is the largest of them all. It spans an area larger than all of Earth's continents combined, and it is constantly moving northwestward. Along nearly its entire boundary, it interacts with other plates in ways that produce instability. In many places, the Pacific Plate is made of dense oceanic crust. When it meets lighter continental crust, it is forced downward into the mantle in a process known as subduction. As the plate sinks, it heats up, releases water, and partially melts. This molten material rises toward the surface, feeding volcanic systems above. This is why chains of volcanoes often form parallel to deep ocean trenches. The trench marks where the plate dives downward. The volcanoes mark where magma finds a path back to the surface. Earthquakes occur for a different but related reason. As plates push against one another, friction locks them in place. Stress accumulates silently. When the pressure becomes too great, the plates slip suddenly, releasing energy as seismic waves that travel through the Earth. Some of these earthquakes are barely noticeable. Others can last minutes, shifting the ground by several feet and triggering tsunamis that cross entire oceans. The Ring of Fire is not a perfect circle, nor is it continuous. There are gaps where plate boundaries behave differently, and regions where volcanic activity has gone dormant. But taken as a whole, it represents the most active geological system on the planet. What makes the Ring of Fire especially fascinating is not just its power, but its consistency. For hundreds of millions of years, as continents drifted and oceans opened and closed, this zone of activity has migrated but never disappeared. It is a reminder that the Earth beneath us is not solid in the way it appears. It is dynamic, restless, and always changing, even when the surface feels still. As we move deeper into this lesson, we will begin to slow our focus. We will look closely at how these forces operate beneath the surface, layer by layer, and how the slow movements of rock can shape the world we know. For now, let the idea settle. A vast ring, unseen but ever-present, quietly shaping coastlines, mountains, and oceans, while most of the world sleeps. Chapter 2: Plates in Motion. To understand the Pacific Ring of Fire more deeply, we need to slow down and imagine the Earth not as a solid sphere, but as a layered system in constant motion. Beneath the oceans and continents lies the mantle, a vast region of hot, dense rock that behaves neither like a solid nor a liquid. Over immense spans of time, this rock flows slowly, carrying heat from the deep interior of the planet toward the surface. Floating above it is the lithosphere, broken into tectonic plates that drift atop this moving foundation. These plates do not glide smoothly. Their edges are jagged, irregular, and often locked together by friction. The motion that drives them comes from heat deep within the Earth, generated by radioactive decay and residual energy from the planet's formation. This heat creates convection currents in the mantle, rising and sinking in slow rolling cycles that push and pull the plates above. The Pacific Plate sits at the center of this system. It is surrounded almost entirely by other plates, making its boundaries some of the most complex and active on Earth. Unlike continental plates, the Pacific Plate is primarily oceanic, meaning it is thinner and denser. This single fact explains much of the violence associated with the Ring of Fire. When two plates meet, the nature of their interaction depends on their density and direction of movement. Along much of the Ring of Fire, the Pacific Plate collides with continental or less dense oceanic plates. Because it is heavier, it is forced downward, sliding beneath the opposing plate and sinking into the mantle. This process is known as subduction, and it is one of the most important mechanisms shaping the Earth's surface. As a plate descends, it does not simply disappear. Water trapped in minerals within the oceanic crust is released as the plate heats up. This water lowers the melting point of the surrounding mantle, allowing magma to form. Over time, this magma rises, accumulating in chambers beneath the surface until it finds a path upward. Volcanoes above subduction zones often form long chains, each one marking a place where molten rock has breached the crust. These volcanoes can remain quiet for centuries, only to awaken suddenly when pressure becomes too great to contain. Not all plate boundaries along the Ring of Fire involve subduction. In some areas, plates slide horizontally past one another. These are known as transform boundaries. Here, crust is neither created nor destroyed. Instead, stress builds as plates grind together, releasing energy in sharp, shallow earthquakes. These earthquakes tend to be especially destructive because they occur close to the surface. There is little warning, and the shaking can be intense even when the rupture itself is relatively short. In other regions, plates pull apart. Magma rises to fill the gap, creating new crust. While this type of boundary is less common along the Ring of Fire, it plays a role in shaping certain volcanic arcs and ocean basins connected to the Pacific. What ties all of these boundaries together is movement without rest. Plates are always shifting, even when nothing appears to be happening. Mountains grow millimeter by millimeter. Trenches deepen imperceptibly. Stress accumulates in silence. Human timescales struggle to capture this motion. A fault that slipped several meters during an earthquake may have been locked for hundreds of years. A volcano that erupts violently may have spent centuries quietly collecting magma beneath the surface. From space, the Pacific Ring of Fire would not appear as a glowing band or a line of smoke. It would look calm, blue, and still. Its true activity is hidden beneath the surface, detectable only through instruments, subtle ground movements, and the occasional dramatic release of energy. Understanding plate motion helps explain why the Ring of Fire is not evenly active. Some regions experience constant low-level earthquakes, relieving stress gradually. Others remain deceptively quiet, accumulating energy that will one day be released in powerful events. This uneven rhythm gives the Ring of Fire its unpredictable nature. It is not chaotic, but it does not operate on schedules humans can easily perceive. As you listen, imagine the Earth breathing slowly beneath you, plates drifting, colliding, sinking, and rising in a cycle that is repeated for hundreds of millions of years. In the next chapter, we will follow one of these boundaries more closely, tracing how subduction zones shape coastlines, island chains, and some of the most dramatic landscapes on Earth. Chapter 3, where plates descend. Along the Pacific Ring of Fire, some of the most powerful geological forces on Earth are concentrated in narrow, hidden zones where one tectonic plate sinks beneath another. These regions, known as subduction zones, are responsible for many of the world's deepest ocean trenches, its most explosive volcanoes, and its largest earthquakes. At the surface, a subduction zone may appear calm. Waves roll overhead. Coastlines look stable. Cities grow, ports expand, and daily life continues with little sign of what lies below. Yet beneath the ocean floor or continental edge, massive slabs of rock are slowly bending downward, sliding into the mantle under immense pressure. The descent begins where two plates converge. As the denser oceanic plate approaches a lighter plate, it begins to flex. This bending creates a long, narrow depression in the sea floor called a trench. Some trenches along the Ring of Fire plunge more than 6 miles deep, making them the deepest places in the ocean. As the plate sinks, it drags sediments and seawater with it. Minerals that formed in the cold depths of the ocean floor are suddenly exposed to intense heat and pressure. Over time, chemical changes occur. Water is released from the descending plate, rising into the mantle above. This release of water plays a critical role. It lowers the melting point of the surrounding rock, allowing magma to form at depths where solid rock would otherwise remain stable. This magma is buoyant. It rises slowly, collecting in reservoirs beneath the crust. The journey upward is rarely direct. Magma may stall, cool, or crystallize before reaching the surface. Some never erupts at all, becoming part of the continental crust. Others find fractures and weaknesses, eventually feeding volcanoes that rise above the landscape. The type of volcano that forms depends on the nature of the magma and the structure of the crust. Along subduction zones, volcanoes tend to be steep-sided and explosive. Their magma is rich in silica and gas, making eruptions more violent and unpredictable. These volcanoes often appear in arcs, forming curved chains that mirror the shape of the trench below. The distance between trench and volcano reflects how deep the plate has descended before melting begins. Earthquakes accompany every stage of this process. Near the surface, plates may lock together, building stress. Deeper down, as the descending plate bends and fractures, earthquakes occur at increasing depths. Some can be detected hundreds of miles beneath the surface. This creates a sloping plane of seismic activity, tracing the path of the sinking plate. Scientists use these patterns to map subduction zones deep within the Earth, even where the surface gives no clues. The largest earthquakes on Earth occur along subduction zones. When vast sections of a plate boundary rupture at once, the released energy can shift the seafloor dramatically. If this movement displaces water, it can generate tsunamis that travel across entire ocean basins. These waves move quickly and quietly in deep water, only rising into destructive walls of water as they approach shallow coastlines. The source may be thousands of miles away, yet the impact can be sudden and severe. Despite their dangers, subduction zones are also creators. They recycle oceanic crust back into the mantle, drive the growth of continents, and supply the nutrients that support fertile soils near volcanic regions. Over geological time, these zones have shaped the Pacific Rim, lifting mountain ranges, forming island chains, and determining where land meets sea. As you picture these processes, imagine them unfolding in slow motion, plates bending, sinking, heating, and melting over millions of years. Energy building quietly, then releasing in moments that leave lasting marks on the surface. In the next chapter, we will shift our focus to the volcanoes themselves, exploring how they form, how they erupt, and why the Ring of Fire contains so many of the world's most active volcanic systems. Chapter 4. The Architecture of Volcanoes. Volcanoes along the Pacific Ring of Fire are not random features scattered across the landscape. They are carefully placed by geology, each one marking a point where forces deep within the earth have found a pathway to the surface. While volcanoes come in many forms, those associated with the Ring of Fire tend to share certain characteristics shaped by subduction. Their structure, behavior, and even their long periods of quiet all reflect the processes unfolding far below them. At the heart of every volcano lies magma. This molten rock forms deep within the mantle or lower crust, created by heat, pressure, and the presence of water released from descending plates. As magma rises, it encounters cooler rock, causing gases dissolved within it to expand. These gases include water vapor, carbon dioxide, and sulfur compounds. When magma is thick and sticky, gases struggle to escape. Pressure builds. When release finally occurs, eruptions can be sudden and violent. This is why many Ring of Fire volcanoes are stratovolcanoes, also known as composite volcanoes. They are tall, steep-sided mountains built from alternating layers of lava flows, ash, and volcanic debris. Each layer records a past eruption, a snapshot of pressure released and rebuilt over time. Between eruptions, these volcanoes can appear peaceful. Snow may cap their summits. Forests grow along their slopes. Towns and cities settle nearby, drawn by fertile soils enriched by volcanic ash. Yet beneath the surface, magma may be slowly accumulating. Small earthquakes and subtle ground swelling often signal this hidden activity. The volcano is not dormant, only resting. Eruptions from stratovolcanoes can take many forms. Some begin with explosive blasts that send ash high into the atmosphere. Others produce pyroclastic flows, fast-moving clouds of hot gas and debris that race down slopes, reshaping everything in their path. Lava flows may follow, moving more slowly, but capable of burying landscapes under thick layers of rock. Over time, these repeated eruptions build the iconic conical shapes associated with many Ring of Fire volcanoes. Not all volcanoes erupt dramatically. Some release magma quietly through fissures, producing gentle lava flows that spread outward rather than building steep peaks. These eruptions still contribute to the growth of land, especially in island arcs where new crust is continually added. The location of volcanoes is not arbitrary. They form at consistent distances from subduction trenches, determined by the depth at which magma generation occurs. This hidden geometry beneath the earth creates visible patterns on the surface. Volcanoes also interact with one another in subtle ways. Magma chambers can be connected through networks of fractures. An eruption at one volcano may alter pressure conditions beneath another, sometimes triggering activity miles away. Over long periods, volcanic systems can migrate. As plates shift and subduction angles change, the zones where magma forms may move inland or offshore, leaving behind extinct volcanoes as silent markers of past activity. These ancient volcanoes often erode into rugged hills or disappear entirely, their presence revealed only through the rocks they leave behind. Despite their destructive potential, volcanoes play a crucial role in Earth systems. They release gases that help regulate the atmosphere. They contribute minerals that support ecosystems. They build land where none existed before. The Ring of Fire is not simply a zone of danger. It is a zone of creation, renewal, and balance, operating on timescales far longer than human history. As you let this chapter settle, imagine the slow rhythm of volcanic systems. Long silence, subtle movement, sudden release, and then quiet again. In the next chapter, we will turn our attention to earthquakes, exploring how stress builds, how faults fail, and why seismic events along the Ring of Fire can be so powerful. Chapter 5, The Language of Earthquakes. Earthquakes are the most frequent expression of the Pacific Ring of Fire's activity. Unlike volcanoes, which announce themselves through visible mountains and eruptions, earthquakes are largely invisible until the moment they occur. They are the sudden release of energy that has been quietly accumulating deep within the earth. Along the Ring of Fire, tectonic plates are rarely free to move smoothly. Their edges catch, lock, and resist motion due to friction. Even as the plates continue to push, pull, or slide past one another, the boundary between them may remain stuck. Stress builds slowly, almost imperceptibly, as rock begins to deform under pressure. This stored energy can remain trapped for years or centuries. To those living above it, the ground feels solid and unmoving. Yet at a microscopic level, minerals are bending, compressing, and straining beyond their natural limits. Eventually, the strength of the rock is exceeded. The fault slips. In a fraction of a second, stored energy is released and radiates outward as seismic waves. This is an earthquake. These waves travel through the earth in different ways. Some move by compressing and expanding rock, while others shear it side to side. When they reach the surface, they cause the shaking felt during an earthquake. The strength of shaking depends on many factors. The size of the rupture matters, but so does its depth. Shallow earthquakes tend to cause more damage because seismic waves have less distance to travel before reaching the surface. Along the Ring of Fire, many earthquakes occur at shallow depths near plate boundaries. Others originate deep within subducting plates, hundreds of miles beneath the surface. These deep earthquakes are rarely destructive, but they reveal the presence of descending slabs far below the crust. Earthquakes along subduction zones can be especially powerful. When large sections of a plate boundary rupture at once, the movement can involve hundreds of miles of fault slipping by several meters. These are the earthquakes capable of reshaping coastlines and altering landscapes permanently. Some of the most dangerous earthquakes occur offshore. When the seafloor is suddenly lifted or dropped, it displaces massive volumes of water. This displacement can generate tsunamis that travel across the Pacific at jetliner speeds. Unlike surface waves, tsunami waves pass unnoticed in deep water. Ships may barely feel them. Only as the waves reach shallow coastal areas do they slow down, rise, and surge inland with devastating force. Not all earthquakes strike without warning. Many are preceded by foreshocks, smaller earthquakes that occur as stress begins to release. Others are followed by aftershocks, which can continue for weeks or months as the crust adjusts to its new position. Scientists study these patterns closely using dense networks of seismometers placed around the Ring of Fire. These instruments record vibrations too small for humans to feel, revealing constant motion beneath the surface. Despite advances in monitoring, precise earthquake prediction remains beyond reach. Scientists can identify regions of high risk and estimate long-term probabilities, but the exact timing of an earthquake cannot be known in advance. This uncertainty is part of what makes earthquakes so unsettling. They remind us that the ground beneath our feet is not fixed, but dynamic. Yet earthquakes also serve an important role. They release built-up stress, preventing even larger ruptures. They shape mountains, deepen trenches, and help drive the ongoing evolution of the Earth's surface. As you listen, imagine the Earth slowly stretching and tightening like a loaded spring. Long periods of quiet, punctuated by brief moments of release. In the next chapter, we will explore how the Pacific Ring of Fire influences human history, shaping civilizations, cultures, and the ways people have learned to live alongside a restless planet. Chapter 6. Mechanics beneath the crust. To move into a more technical understanding of the Pacific Ring of Fire, we need to shift our attention downward, away from surface expressions like volcanoes and earthquakes, and into the physical mechanics that govern plate behavior at depth. The lithosphere is not a uniform shell. It consists of the crust and the rigid uppermost mantle, varying in thickness from less than 100 kilometers beneath oceans to more than 200 kilometers beneath continents. Below it lies the asthenosphere, a hotter, weaker region of the upper mantle that deforms plastically over geological time. It is this mechanical contrast, rigid plates above and ductile mantle below, that allows plate tectonics to operate at all. Motion along the Ring of Fire is primarily driven by slab pull. As dense oceanic lithosphere cools with age, it becomes negatively buoyant relative to the surrounding mantle. When it begins to subduct, gravity takes over, pulling the rest of the plate downward and forward. This force is stronger than ridge push, the gravitational sliding of plates away from mid-ocean ridges. In fact, slab pull is considered the dominant driver of plate motion for the Pacific Plate and its surrounding boundaries. As a subducting slab descends, it does not remain intact indefinitely. Temperature and pressure increase with depth, but not uniformly. Oceanic lithosphere entering a subduction zone is cold relative to the surrounding mantle, allowing it to remain rigid to depths of several hundred kilometers. Within this depth range, the slab undergoes metamorphic phase changes. Minerals rearrange their crystal structures in response to increasing pressure, often becoming denser. These transformations release bound water into the overlying mantle wedge. This dehydration process is fundamental. The addition of water lowers the solidus temperature of mantle peridotite, enabling partial melting at depths typically between 80 and 150 kilometers. The resulting melts are basaltic at depth, but evolve chemically as they rise through the crust. As magma ascends, it undergoes fractional crystallization, assimilation of surrounding rock, and magma mixing. These processes increase silica content and volatile concentration, producing the andesitic to dacitic compositions characteristic of many Ring of Fire volcanoes. From a mechanical perspective, subduction zones are divided into distinct coupling regimes. Near the surface, the plate interface is often locked due to friction and low temperatures. This is the seismogenic zone, where elastic strain accumulates and is released in megathrust earthquakes. Below this region, increasing temperature causes the interface to transition from stick-slip behavior to stable sliding. Deeper still, the slab deforms ductilely, producing intermediate and deep focus earthquakes through mineral phase transformations rather than brittle failure. These deep earthquakes, sometimes exceeding 600 kilometers in depth, were once thought impossible. Their existence provided key evidence that subducting slabs penetrate far into the mantle rather than stagnating at shallow depths. Seismic tomography has since confirmed this. By analyzing the speed of seismic waves traveling through the Earth, scientists can image cold, fast-moving slabs descending beneath the Ring of Fire. These images reveal slabs folding, tearing, and in some cases penetrating into the lower mantle. Such behavior influences surface geology. Slab geometry affects volcanic arc location, earthquake distribution, and even topography. A steeply dipping slab produces a narrow, volcanic arc close to the trench, while a shallow slab can suppress volcanism altogether and transmit stress far inland. Transform boundaries along the Ring of Fire operate under different mechanics. Here, plates are laterally offset, and deformation is localized along near-vertical fault zones. Stress accumulates elastically until frictional resistance is overcome, producing strike-slip earthquakes. The mechanical properties of faults vary with depth, temperature, and fluid pressure. Elevated pore fluid pressure can reduce effective normal stress, allowing faults to slip more easily and influencing earthquake frequency and magnitude. Taken together, these processes form a coupled system. Plate motion, thermal structure, fluid release, chemical evolution, and mechanical deformation are all linked. Changes in one part of the system propagate through the rest. The Pacific Ring of Fire is therefore not simply a boundary, but a dynamic interface between Earth's interior and surface. It is where energy from the planet's formation and ongoing heat production is transferred upward, shaping landscapes and driving geological hazards. As this chapter settles, imagine the Earth not as layers stacked neatly, but as a continuously interacting system. Cold slabs sinking, hot mantle rising, fluids migrating, stress accumulating, and energy releasing in precise physical ways. Chapter 7, Feedbacks and Deep Time Evolution. The Pacific Ring of Fire is often described as a boundary, but this description is misleading. It is not a simple line where plates meet, nor a static feature fixed in space. Instead, it is a long-lived, evolving system produced by feedbacks between the lithosphere, mantle, surface processes, and deep planetary heat. To understand why the Ring of Fire exists in its present form, we must move beyond individual volcanoes or earthquakes and instead examine how tectonic systems evolve through deep time. Plate tectonics operates because Earth is losing heat. From the moment the planet formed, it began cooling, and that cooling continues today. Heat escapes from the interior through conduction, convection, volcanism, and plate motion. The Ring of Fire is one of the most efficient pathways for this heat loss, making it central to the planet's long-term thermal evolution. Oceanic lithosphere plays a key role in this process. It is continuously created at mid-ocean ridges, where upwelling mantle partially melts and solidifies into basaltic crust. At the moment of formation, this crust is hot, thin, and relatively buoyant. But as it moves away from the ridge, it begins to cool. Cooling thickens the lithosphere. As temperature decreases, the mantle portion of the plate becomes mechanically stronger and denser. Over tens of millions of years, oceanic lithosphere undergoes a transformation from a buoyant, flexible structure into a cold, rigid slab capable of sinking into the mantle. This transformation is slow, steady, and inevitable. Once oceanic lithosphere becomes sufficiently dense, subduction becomes thermodynamically favorable. Gravity, rather than horizontal compression, becomes the dominant driver of motion. When a plate begins to sink, it does not simply slide downward. It pulls the rest of the plate behind it. This force, known as slab pull, is the most powerful driver of plate motion on Earth. In the Pacific Basin, slab pull dominates over ridge push and basal drag. The configuration of the Ring of Fire, where the Pacific plate is surrounded by subduction zones, reflects this dominance. The plate is being consumed along much of its margin, pulled downward by its own weight. Once subduction initiates, it introduces a powerful positive feedback. Faster plate motion increases convergence rates. Increased convergence enhances deformation along the plate boundary. Greater deformation promotes fracturing, fluid migration, and chemical reactions within the subducting slab. As the slab descends, it undergoes a series of metamorphic transformations. Minerals stable at low pressure and temperature become unstable as conditions change. Hydrous minerals break down, releasing water into the surrounding mantle. This dehydration is not incidental. It is central to sustaining volcanic arcs. The released fluids rise into the mantle wedge above the slab, lowering the melting temperature of mantle rocks. Partial melting becomes possible at depths where dry mantle would remain solid. The resulting melts ascend, evolve chemically, and eventually feed volcanic systems at the surface. This process links plate motion directly to volcanism. Faster subduction delivers more slab material into the mantle. More slab material produces more fluids. More fluids generate more melt. More melt sustains volcanic arcs. The system reinforces itself. However, this reinforcement is not limitless. The Earth imposes constraints, and over time, negative feedbacks emerge. One of the most important constraints lies deep within the mantle. As slabs descend, they encounter mineral phase boundaries that alter their buoyancy and mechanical behavior. At depths near 410 kilometers and 660 kilometers, changes in mineral structure produce density contrasts that can impede slab motion. In many regions beneath the Ring of Fire, slabs do not sink smoothly into the lower mantle. Instead, they flatten within the mantle transition zone. Seismic tomography has revealed extensive slab stagnation beneath parts of East Asia, the Western Pacific, and the Americas. When slabs stagnate, slab pull weakens. The plate loses one of its primary driving forces. Convergence rates slow. Stress distribution along the plate boundary changes. Volcanic arcs may migrate landward or seaward, or shut down entirely. These changes are not immediate. They unfold over millions of years, producing gradual shifts in the location and intensity of tectonic activity. What appears as a stable volcanic arc on human timescales may in fact be in the process of slow migration or decline. Subduction also modifies the overriding plate in ways that eventually resist further subduction. Sediments scraped from the downgoing plate accumulate in accretionary wedges, thickening continental margins. Magma generated above the slab intrudes into the crust, forming plutons and underplated layers that increase crustal thickness. Over time, this process transforms the composition and buoyancy of continental crust. Thickened felsic crust is resistant to being subducted. As buoyancy increases, the mechanical coupling between plates changes. Subduction may become less efficient or more localized. This resistance can trigger tectonic reorganization. Trenches may retreat seaward. Subduction zones may jump to new locations. In some cases, subduction ceases entirely, converting an active margin into a passive one. The Ring of Fire has experienced multiple such reorganizations throughout Earth's history. Ancient volcanic arcs now exist far inland, preserved as mountain belts and metamorphic complexes. These features record former positions of subduction zones long vanished. Mantle convection exerts additional control over this evolution. Subducting slabs act as long-lived cold downwellings, shaping mantle flow patterns on a global scale. These downwellings can stabilize plate boundaries by anchoring them to deeper mantle structures. Conversely, slab tearing or breakoff can destabilize entire regions. Slab breakoff occurs when the descending portion of a plate detaches from the portion still attached to the surface. This detachment abruptly removes slab pull, triggering rapid changes in stress distribution. Such events can produce uplift of the overriding plate, pulses of magmatic activity, and reorganization of fault systems. Geological records around the Pacific suggest that slab breakoff has played a role in several major tectonic transitions. Fault systems evolve alongside these deep processes. Repeated earthquake rupture damages rock, creating complex fault networks and altering permeability. Fluids migrate through these networks, influencing fault strength and rupture behavior. Over time, faults may transition from simple planar structures to complex systems with multiple strands, stepovers, and locked segments. This complexity affects how earthquakes propagate and why seismic behavior varies so dramatically along the Ring of Fire. Volcanic systems also evolve chemically and structurally. Early arc volcanism tends to produce relatively mafic compositions, reflecting direct melting of the mantle wedge. Over time, repeated melting, differentiation, and crustal assimilation yield increasingly silica-rich magmas. This chemical evolution is not merely a detail. It reflects long-term coupling between mantle processes and crustal growth. As crust thickens and becomes more evolved, it changes how magma ascends, stalls, and erupts. These evolving systems feed back into surface processes. Volcanic construction alters topography. Mountain building changes erosion patterns. Increased erosion delivers sediments to trenches, affecting subduction dynamics. Surface processes influence deep ones. Sediment loading affects stress distribution in the crust. Erosion alters lithospheric thickness. Changes in sea level modify pressure at plate boundaries. The system is fully coupled. No part operates in isolation. When viewed through deep time, the Pacific Ring of Fire is revealed not as a static ring, but as a migrating, evolving zone of energy transfer. Its shape, intensity, and location have changed repeatedly, and they will continue to change in the future. The modern Ring of Fire is simply the current configuration of a system that has existed in various forms for hundreds of millions of years. It reflects the present balance between plate buoyancy, mantle flow, crustal growth, and planetary cooling. Understanding this evolution reframes how we think about geological hazards. Earthquakes and volcanoes are not random events. They are expressions of long-term processes operating within a constrained physical system. The Ring of Fire persists because it efficiently transfers heat and material from Earth's interior to its surface. As long as the planet continues to cool, systems like it will continue to exist. As this chapter settles, the key idea is continuity rather than permanence. The Ring of Fire is not fixed, but it is persistent. It moves, reorganizes, weakens, and strengthens, guided by the physics of a cooling planet. What we observe today is not an endpoint, but a moment within a much longer story, written slowly beneath the surface, one slab at a time. Chapter 8. A Dynamic Planet in Balance. The Pacific Ring of Fire is often described as Earth's most dangerous region, but danger is a human framing. From a planetary perspective, the Ring of Fire is not a zone of instability or failure. It is one of the primary mechanisms through which the Earth regulates itself. It exists because the planet is active, cooling, and continuously reorganizing its interior and surface in response to fundamental physical laws. To understand the Ring of Fire in this broader context, we must step back from individual tectonic processes and consider Earth as a thermodynamic system. The planet contains an enormous amount of internal heat, retained from its formation and supplemented by the ongoing decay of radioactive elements within the mantle and crust. This heat cannot remain trapped indefinitely. It must move upward and outward. The movement of this heat drives mantle convection, plate tectonics, volcanism, and seismicity. The Ring of Fire is one of the most efficient expressions of this energy transfer. It is where cold lithosphere sinks, hot mantle rises, and material is continuously exchanged between Earth's surface and interior. Subduction zones are central to this exchange. When oceanic lithosphere descends into the mantle, it carries with it surface materials, including sediments, water, carbon, and other volatiles. These materials are not lost. They are redistributed within the mantle, stored temporarily in mineral phases, and eventually returned to the surface through volcanism. This recycling process links deep Earth dynamics to surface environments in ways that extend far beyond geology. It influences the composition of the atmosphere, the chemistry of the oceans, and the long-term stability of Earth's climate. Volcanic degassing along the Ring of Fire releases water vapor, carbon dioxide, sulfur compounds, and trace gases into the atmosphere. While individual eruptions can disrupt ecosystems and human societies, the cumulative effect of volcanic degassing over geological timescales is regulatory rather than destructive. Carbon dioxide released by volcanoes plays a critical role in Earth's long-term carbon cycle. Over millions of years, volcanic emissions balance carbon removed from the atmosphere through weathering and sediment burial. This balance helps maintain surface temperatures within a range that allows liquid water to persist. Without sustained volcanic outgassing, Earth's atmosphere would gradually lose carbon dioxide to chemical weathering. Global temperatures would fall, potentially pushing the planet toward a permanently frozen state. The Ring of Fire, through continuous degassing, helps prevent this outcome. Water cycling is equally important. Subduction transports water deep into the mantle, where it is stored in hydrous minerals. Some of this water returns to the surface through arc volcanism. This deep water cycle helps regulate the volume of surface oceans and influences mantle viscosity and melting behavior. The Ring of Fire therefore participates in maintaining Earth's habitability. It is not merely a source of hazards, but a component of a planetary system that supports long-term surface stability. Earthquakes play a complementary role. From a human perspective, earthquakes are sudden, violent, and destructive. From a mechanical perspective, they are a necessary consequence of plate motion. They represent the release of elastic strain accumulated as plates resist movement along their boundaries. Without earthquakes, plates would still move, but stress would accumulate to unsustainable levels. Failure would occur less frequently, but far more catastrophically. Earthquake slip allows plates to move incrementally, maintaining long-term motion within physical limits. Along the Ring of Fire, earthquakes occur across a wide range of depths and mechanisms. Shallow earthquakes reflect brittle failure in the upper crust. Intermediate and deep earthquakes reflect deformation within subducting slabs under extreme pressure. Together, these events map the internal structure of the Earth, Seismic waves generated by earthquakes provide the primary means by which scientists image the deep interior. In this way, earthquakes are not only mechanical adjustments, but sources of information that reveal the planet's internal architecture. Mountain building along the Ring of Fire further illustrates the coupling between tectonics and surface systems. Convergence and subduction thicken crust, uplift mountain ranges, and create complex topography. This topography alters atmospheric circulation, precipitation patterns, and erosion rates. Increased erosion delivers sediments to rivers, deltas, and eventually trenches. These sediments influence subduction dynamics by modifying friction along the plate interface and contributing to accretionary wedges. Surface processes feed back into tectonic ones. Sea level is also affected. Subduction recycles dense oceanic crust, while volcanism and crustal growth build buoyant continental landmasses. Over geological time, this redistribution of mass influences the volume and shape of ocean basins, altering global sea level. The Ring of Fire, therefore, shapes not only where earthquakes and volcanoes occur, but where continents rise, oceans deepen, and climates evolve. One of the most important lessons of the Ring of Fire is the scale mismatch between human experience and planetary processes. Earth operates on timescales that dwarf recorded history. Plate motions measured in centimeters per year accumulate into thousands of kilometers over tens of millions of years. A fault that ruptures in seconds may have been locked for centuries. A volcano that erupts violently may have spent tens of thousands of years accumulating magma. These disparities in timescale make geological processes difficult to intuit. This mismatch also limits predictability. While the physics governing rock deformation and fluid flow are well understood, tectonic systems involve enormous spatial domains and long histories of accumulated damage, heterogeneity, and feedback. Small variations in temperature, fluid pressure, or rock composition can alter outcomes dramatically. As a result, precise prediction of earthquakes and eruptions remains beyond current capability. Instead, scientists rely on probabilistic assessments that estimate likelihood rather than certainty. Modern monitoring has greatly improved our understanding of the Ring of Fire. Dense seismic networks track constant microseismic activity. Satellite measurements detect ground deformation at millimeter scales. Gas monitoring reveals changes in volcanic systems long before eruptions occur. These tools reveal a planet in constant motion, even when the surface appears calm. They show that tectonic systems are never truly inactive. They are always adjusting, redistributing stress, and responding to internal and external forces. What emerges from this understanding is a view of Earth as a self-organizing system. The Ring of Fire is not an anomaly. It is a natural outcome of how a rocky planet cools, convects, and differentiates over billions of years. Planets without plate tectonics behave differently. Without subduction, heat loss is less efficient. Volcanism becomes episodic rather than continuous. Surface environments evolve along different trajectories. The presence of a system like the Ring of Fire may be one of the factors that distinguishes Earth from other rocky worlds. For human societies, the Ring of Fire presents a challenge. Communities along its margins must adapt to geological risk, incorporating hazard awareness into infrastructure, planning, and culture. These adaptations represent an ongoing negotiation between short human lifespans and long planetary processes. From the planet's perspective, however, this negotiation is incidental. The Ring of Fire does not respond to human activity. It responds to gravity, heat, pressure, and chemistry. Its rhythms are set by forces that operate far beneath the surface. The most important insight is not danger, but continuity. The same processes that generate earthquakes and volcanoes also create continents, recycle oceans, regulate climate, and sustain a dynamic surface capable of supporting life. The Pacific Ring of Fire is not separate from Earth. It is one of the ways Earth expresses itself. As this final chapter settles, imagine the planet not as a static sphere, but as a system in motion. Plates drift slowly. Slabs sink, heat rises, material cycles endlessly between surface and interior. These processes continue whether they are observed or not. They continue beneath quiet oceans and sleeping cities, shaping the world incrementally, relentlessly, and without pause. The Ring of Fire is not an ending or a warning. It is evidence of a living planet, still active, still cooling, and still writing its history deep beneath the surface. Chapter 9. Futures of the Ring of Fire across geological time. Predicting the future of the Pacific Ring of Fire requires abandoning human intuition about time. The processes that govern tectonics do not respond to decades or centuries. They respond to tens of thousands, millions, and tens of millions of years. When viewed through this lens, the future of the Ring of Fire is not speculative in the casual sense. It is constrained by physical laws, boundary conditions, and measurable plate motions already underway. The uncertainty lies not in whether change will occur, but in how those changes will express themselves spatially and temporally. To explore this future, it is useful to examine three distinct timescales. The first spans approximately 100,000 years, a period long enough for measurable tectonic and volcanic change, but short relative to plate reorganization. The second spans 1 million years, a scale at which plate geometry, slab behavior, and volcanic arcs begin to migrate meaningfully. The third spans 10 million years, a duration over which the Ring of Fire itself may no longer resemble its modern configuration. Each timescale reveals a different aspect of Earth's long-term evolution. The next 100,000 years intensification without reorganization. On a timescale of 100,000 years, the overall geometry of the Pacific Ring of Fire will remain largely intact. The Pacific Plate will continue to move northwestward at rates on the order of 7 to 10 centimeters per year. Over 100,000 years, this motion amounts to several kilometers, enough to alter stress distributions but not enough to fundamentally reshape plate boundaries. Subduction zones will remain active along the Western Americas, the Aleutian Arc, Japan, the Philippines, Indonesia, and New Zealand. Existing volcanic arcs will persist. Trenches will deepen incrementally. Earthquake cycles will continue to repeat. The most significant changes during this interval will occur through accumulation rather than transformation. Stress will continue to build along locked segments of major subduction interfaces. Regions such as the Cascadia subduction zone, the Nankai Trough, the Chilean margin, and parts of the Sunda megathrust are already storing elastic strain. Over 100,000 years, multiple megathrust earthquakes will almost certainly occur along each of these systems. These events will not be anomalies. They will be the expected mechanical release of long-term convergence. Volcanic systems will respond to these tectonic rhythms. Some volcanoes currently considered dormant will likely erupt. Others will cease activity as magma supply pathways evolve. Volcanic output along arcs will fluctuate as slab dehydration fronts migrate downward and laterally. Magmatic systems will evolve chemically during this period. Continued crustal assimilation and fractional crystallization will favor more silica-rich magmas in mature arcs. Explosive volcanism will remain characteristic of many Ring of Fire regions. From a surface perspective, coastlines will change subtly. Earthquake-driven uplift and subsidence will reshape shorelines. Tsunami deposits will accumulate along vulnerable margins. Mountain ranges will grow incrementally as convergence continues. Importantly, climate will interact with these processes. Over the next 100,000 years, Earth is likely to experience additional glacial interglacial cycles. Changes in ice volume will redistribute surface loads, subtly altering stress on faults and influencing earthquake timing. This interaction is well documented in the geological record. Glacial unloading can increase seismicity in tectonically active regions. Thus, future climate cycles may modulate seismic behavior along parts of the Ring of Fire. Despite these changes, the ring itself will remain recognizable. The system will intensify, relax, and pulse, but not reorganize. 1 million years migration, slab evolution, and arc adjustment. On a timescale of 1 million years, the Ring of Fire begins to show meaningful structural change. At this scale, plate motion becomes impossible to ignore. The Pacific plate will have moved tens of kilometers. Subducting slabs will have descended deeper into the mantle. Mantle wedge conditions will evolve in response to changing thermal and chemical gradients. One of the most important processes during this interval will be slab rollback. As subducting slabs sink, they tend to retreat trenchward due to gravitational forces and mantle flow. This retreat can cause volcanic arcs to migrate landward or seaward depending on local geometry. In regions where slab rollback dominates, back arc extension may increase. This could lead to the formation of new rift basins or back arc spreading centers, particularly in the Western Pacific. Portions of the Philippine sea plate and adjacent microplates may undergo further fragmentation. In contrast, regions with shallow slab subduction may experience volcanic shutdown. Shallow slabs reduce mantle wedge melting by limiting asthenospheric flow. This phenomenon is already observed beneath parts of South America. Over 1 million years, similar conditions could develop elsewhere. Slab stagnation within the mantle transition zone will become more pronounced. As slabs accumulate near the 660-kilometer boundary, their negative buoyancy decreases. This will gradually reduce slab pull forces. As slab pull weakens, plate convergence rates may slow. This deceleration will not be uniform. Some segments of the Ring of Fire may remain highly active, while others enter periods of relative quiescence. Earthquake behavior will reflect this heterogeneity. Locked segments may persist longer between ruptures. Other regions may experience more frequent, lower magnitude seismicity as stress is released more continuously. Volcanic arcs will continue to evolve chemically. Over 1 million years, crustal thickening beneath arcs will become significant. This thickening alters magma storage depths, eruption styles, and eruption frequency. Some volcanic chains may become extinct. Others may initiate new centers as magma pathways reorganize. The surface expression of volcanism will shift accordingly. At the continental scale, accretion will continue. Terranes will be added to continental margins. Mountain belts will grow. Sediment delivery to trenches will increase, further influencing subduction dynamics. The Ring of Fire at 1 million years in the future will still exist, but it will not be identical to the present-day system. It will be offset, reshaped, and uneven in intensity. 10 million years, reorganization and the beginning of closure. At 10 million years, the future of the Ring of Fire enters a different regime entirely. This is the time scale over which tectonic systems reorganize. The Pacific plate is shrinking. It is being consumed faster than it is being created. Over tens of millions of years, this imbalance will lead to the gradual closure of the Pacific basin. 10 million years from now, this closure will be well underway. Subduction along the Americas will continue, but the geometry of the plate boundary may change significantly. Slab break-off events are likely as increasingly buoyant lithosphere resists subduction. These break-offs will trigger uplift, magmatic flare-ups, and changes in stress orientation. In the Western Pacific, continued back arcs spreading may fragment existing plates further. New microplates will form. Old ones will be consumed. The complexity of plate interactions will increase before ultimately simplifying. One of the most likely long-term outcomes is the initiation of new subduction zones within the Pacific basin itself. Intraplate subduction initiation is rare, but it becomes more probable as plate geometry evolves and compressional stresses increase. Such initiation events would mark the beginning of a fundamental reorganization of the Ring of Fire. Volcanic activity will migrate accordingly. Some of today's most active arcs may shut down entirely. New arcs may form where none exist today. The distribution of earthquakes will change. Megathrust systems may be replaced by different styles of convergence. Transform boundaries may evolve into compressional zones. At the mantle scale, accumulated slabs may penetrate the lower mantle more efficiently. This could alter global mantle convection patterns, influencing plate motion on a planetary scale. The Ring of Fire as a continuous structure may begin to fragment. It may no longer appear as a coherent ring, but as a series of evolving tectonic zones. Beyond 10 million years, the fate of the Pacific. Although 10 million years lies beyond intuitive comprehension, it represents only a small fraction of Earth's tectonic future. On longer timescales, the Pacific Ocean is likely to close entirely, as previous superoceans have done. The Ring of Fire would then cease to exist in its current form, replaced by new collision zones, mountain belts, and continental interiors. What replaces it will depend on the configuration of future continents, mantle convection patterns, and the evolving thermal state of the planet. But the process will follow the same physical principles observed today. Lithosphere will cool, slabs will sink, heat will rise, plates will move. The Ring of Fire is not eternal, but plate tectonics is, limits of prediction and confidence in process. While specific outcomes become increasingly uncertain with time, the governing processes are well constrained. Plate motion directions are measured. Slab geometry is imaged. Mantle properties are inferred from seismic data. These constraints allow scientists to project plausible futures, even if precise details remain unknowable. The most important conclusion is not what the Ring of Fire will look like, but how it will behave. It will continue to evolve through feedbacks between gravity, heat, chemistry, and mechanics. It will reorganize when thresholds are crossed. It will persist as long as Earth remains tectonically active. From a planetary perspective, the future of the Ring of Fire is not a question of danger or stability. It is a question of energy transfer and material cycling. The same forces that shaped the ring in the past will shape its future, slowly, inevitably, and far beyond the scale of human time. As this chapter settles, the Earth continues its motion. Plates advance by millimeters. Slabs descend imperceptibly. The future is already unfolding beneath the surface, 1 centimeter, 1 earthquake, 1 eruption at a time. Chapter 10. Living on the Ring of Fire and the Meaning of Risk. If you live on or near the Pacific Ring of Fire, the question of whether you should be worried is not unreasonable. It is also not a question with a simple yes or no answer. From a scientific perspective, the correct response lies somewhere between complacency and fear, grounded in an understanding of probability, preparedness, and scale. The Ring of Fire encompasses hundreds of millions of people. Major cities such as Tokyo, Los Angeles, Santiago, Jakarta, Manila, Seattle, Vancouver, Auckland, and countless others exist because of the same tectonic processes that generate earthquakes and volcanoes. Fertile soils, access to coasts, mountain-fed water systems, and economic corridors are all products of tectonic activity. Human settlement along the Ring of Fire is not accidental. It is the result of long-term geological benefits coupled with short-term geological risks. To understand whether concern is warranted, it is necessary to distinguish between hazard, risk, and vulnerability. Hazard refers to the physical process itself. Earthquakes occur. Volcanoes erupt. Tsunamis propagate. These processes are inevitable along active plate boundaries. They cannot be prevented, slowed, or redirected by human action. Risk, however, is a function of hazard combined with exposure. A powerful earthquake in an uninhabited region presents minimal risk. A moderate earthquake beneath a dense urban area presents significant risk. The same geological process can have radically different consequences depending on where and how people live. Vulnerability refers to how susceptible a population is to damage. Building design, infrastructure resilience, emergency planning, public education, and governance all influence outcomes. From a geological standpoint, living near the Ring of Fire does not mean living in constant danger. Most of the time, tectonic systems release energy gradually. Small earthquakes occur daily. Volcanic systems degas quietly. Stress redistributes without producing destructive events. Large earthquakes and eruptions are rare on human timescales. They are inevitable over geological time, but unlikely in any given year at any specific location. This distinction is critical. Probability, not inevitability, governs individual risk. Modern science allows us to assess this probability with increasing precision. Seismic hazard maps integrate fault geometry, historical rupture patterns, plate motion rates, and stress accumulation. Volcanic hazard assessments consider magma supply rates, eruption history, and geophysical monitoring. These tools do not predict exact events, but they do identify where large events are more likely over long periods. This knowledge informs building codes, land use planning, and emergency preparedness. Japan provides a clear example. It sits atop multiple converging plate boundaries and experiences frequent earthquakes. Yet strict building codes, early warning systems, and public education significantly reduce casualties compared to similar events elsewhere. California follows a similar model. Earthquakes are expected, not feared. Structures are designed to flex rather than resist rigidly. Infrastructure is retrofitted. The risk is acknowledged and incorporated into daily life. In contrast, regions where vulnerability is high often suffer disproportionately from similar hazards. Poor construction, rapid urbanization, limited monitoring, and inadequate emergency response can transform moderate geological events into disasters. Thus, the question is not whether the Ring of Fire is dangerous, but whether human systems are aligned with geological reality. From a scientific perspective, worry is not useful. Awareness is. If you live near an active fault or volcano, the most rational response is to understand the specific hazards of your region. Not all parts of the ring behave the same way. Some regions experience frequent moderate earthquakes. Others store stress for centuries between large ruptures. Some volcanoes erupt regularly. Others may never erupt again. Local geology matters more than global labels. It is also important to understand timescale. Geological hazards operate on intervals that are long relative to human lifespans. A fault with a recurrence interval of 500 years does not pose the same immediate concern as one that ruptures every few decades. Living near the Ring of Fire does not mean living under constant threat. It means living in a place where rare but powerful events are part of the long-term background. From an engineering standpoint, this is a solvable problem. Structures can be designed to withstand shaking. Early warning systems can provide seconds to minutes of notice. Evacuation planning can reduce tsunami risk dramatically. From a psychological standpoint, however, geological risk can feel abstract and unsettling. Earthquakes arrive without warning. Volcanoes challenge intuition about stability. The ground itself feels unreliable. This discomfort is rooted in perception rather than probability. Humans evolved to respond to immediate threats, not low-probability, high-impact events spread across centuries. The mind struggles to calibrate concern appropriately. Science helps bridge this gap by reframing risk quantitatively rather than emotionally. For example, in many Ring of Fire cities, the probability of experiencing a damaging earthquake in any given year is low. Over an entire lifetime, the probability increases, but it is still not certainty, and even when earthquakes occur, most do not result in catastrophic outcomes. Volcanic risk is even more localized. Most volcanoes along the Ring of Fire are monitored continuously. Signs of unrest often appear weeks to months before eruption, allowing for evacuation. Sudden, unanticipated eruptions are rare. Tsunami risk is similarly constrained. Most tsunamis are generated by specific types of earthquakes in specific locations. Warning systems now cover much of the Pacific, providing crucial time for response. From a planetary perspective, none of these processes are malicious or chaotic. They are mechanical outcomes of plate motion. They do not accelerate or intensify because people are present. The Earth does not target. This distinction matters. Living on the Ring of Fire does not place you in an adversarial relationship with the planet. It places you within an active system that operates according to consistent physical laws. Understanding those laws reduces uncertainty. It is also worth recognizing that geological risk exists everywhere, not only along the Ring of Fire. Intraplate earthquakes occur far from plate boundaries. Floods, storms, and wildfires pose risks unrelated to tectonics. No location is risk-free. What distinguishes the Ring of Fire is not danger, but transparency. The processes are visible, studied, and monitored. The risks are known. From a long-term perspective, societies that adapt to geological reality tend to thrive. They incorporate risk into design rather than attempting to ignore it. Over time, this adaptation becomes cultural rather than reactive. If you live near the Ring of Fire, the scientific answer is not to worry, but to be informed. Know your local geology. Understand the hazards specific to your region. Support infrastructure resilience. Participate in preparedness, not fear. The Ring of Fire is not a warning sign. It is a reminder that the earth beneath us is active, dynamic, and alive in a physical sense. For most people, most of the time, it is not a source of danger. It is simply the deep, quiet machinery of a planet that has never been still. As this chapter comes to rest, the ground beneath you continues its slow motion. Plates shift by fractions of a millimeter. Stress redistributes. Heat rises. Life goes on above it. And for those who live on the Ring of Fire, that has always been the case.